Hello, and welcome to Music in the Duomo, Planning a Party. Our 8 animal musicians gave a concert in the Duomo di Milano in Italy. Now, they are going to give a second concert and they would like to have a party afterwards. To plan the party, they need to plan out 3 different things: food, decorations, and music. They decide that they will choose 3 animals to plan these 3 things for the party. Here are the animals. From left to right, they are anteater, beaver, coyote, duck, eagle, flamingo, gorilla, and hare. We will look at 4 different methods of choosing 3 animals to plan out their party. Let's start with our first method. This method is very simple. First, we choose any of the 8 animals to do food. For example, let's say we choose coyote to plan out food. After choosing an animal to do food, we choose an animal to do decorations. We can choose any of the 8 animals, including the animal we chose to do food. In fact, for our example, let's choose coyote to do decorations. So the coyote will do both food and decorations. After choosing animals for both food and decorations, we choose any animal for music. Again, we can choose any of the 8 animals, including either of the 2 animals we have already chosen for food and decorations. In our example, we could choose the coyote to go again, so the coyote will have to plan out food, decoration, and music. But let's choose the gorilla. So we have chosen an animal for food, an animal for decorations, and an animal for music. Using method 1, we had 8 animals to choose from for food. Once we have chosen, we could choose any of the 8 animals again for decorations. Once we have chosen for food and decorations, we have 8 choices for music. So, using method 1, how many ways can we plan out this party? Feel free to pause the video here and try to figure out how many ways we can plan this party using this method. We have 8 choices for planning food, 8 choices for planning decorations, and 8 choices for planning music. And since we plan each thing separately from each other, we get 8 times 8 times 8, or 512 ways to plan the party using method 1. Great. But the musicians decided that they didn't want to have one animal planning 2 different things. So they changed to a different method of assigning animals to tasks. In this method, one animal does not get assigned to 2 different tasks. We'll start out the same with the first method. Any of the 8 animals can be assigned to do food. For our example, we'll have coyote do food, just like in the first method. After choosing an animal to do food, we choose an animal to do decorations. But remember that we're not allowed to have one animal doing 2 different tasks. So there are only 7 animals to plan out decorations. In our example, we are not allowed to choose the coyote to do decorations, because then coyote would be doing both food and decorations, which we do not want. So we can choose any of the other 7 animals. Let's say we chose flamingo to do decorations. Now we choose an animal to do the music. Because coyote is planning out food and flamingo is planning out decorations, we cannot choose them to plan out music, because then they would be doing 2 things. For our example, let's say we choose eagle. So now we have an animal to plan out food, an animal to plan out decorations, and an animal to plan out music. We didn't choose the same animal for 2 tasks. Great! So, using our method, we have 8 choices for food. Once we have chosen, we have 7 other animals to choose from for decorations. Once those 2 are chosen, we have 6 possible choices to plan out music. So, how many ways can we plan out the party using method 2? It's the same as before, but slightly different. Feel free to pause the video here now as you figure out the answer. Since we have 8 choices to choose from for food, 7 choices to plan out decorations, and 6 choices to plan out music, we can take these numbers and multiply them together. 8 times 7 times 6 gives us 336 ways to plan out the party, using method 2. Great! After thinking about it some more, the musicians decide that it would be better to choose 3 different animals and let them decide who does the tasks. So, we're choosing 3 animals to be on the party planning committee. We still have the same rule as last time. It needs to be 3 different animals. They don't want one animal to have 2 votes in the committee. Is this any different from last time? We're still choosing 3 animals, and we still have 8 choices for the first member of the committee, 7 choices for the second member of the committee, and 6 choices for the third member of the committee. But it is different. Pause the video here and try to find out how method 3 is different from method 2. Let's look at our example. With method 2, we chose the coyote, the flamingo, and the eagle. And in method 3, we can choose the same 3 animals to be on our committee, coyote, flamingo, and eagle. So it looks like the same thing. But what if we chose the same 3 animals in a different order? In method 2, that's a different choice. We have the eagle doing food instead of the coyote, we have the coyote doing decorations instead of flamingo, and we have the flamingo doing music instead of the eagle. But in method 3, it's the same choice. The same 3 animals are on the committee each time. The trick is that in method 2, the position of the animal is important. It says which task the animal does. But in method 3, the position of the animal is not important. You're either on the committee or you're not. And mixing up the names on the list doesn't change who's on the committee. In fact, we can agree to always list the animals in alphabetical order, so now the 2 committees look exactly the same. But that's not all of them. There are actually 6 choices in method 2 for each choice in method 3. It's the same as our original calculation for method 2, but there are 3 animals to choose from instead of 8. If we've already chosen the 3 animals on the committee, then there are 3 choices for food, 2 choices for decoration, and 1 choice for music. Multiplying 3 times 2 times 1 gives 6 ways of assigning the tasks to the committee members. So there are 6 choices in method 2 for each choice in method 3. Now you should be able to figure out the number of choices for method 3. Pause the video here and try to find out how many different party committees we can have. So, we know that there are 336 ways to plan out a party using method 2. And we know that 6 of the ways we can choose using method 2 gives us the same planning committee in method 3. Using what we know, we can divide 336 by 6 to see how many different planning committees we can get. This gives us 56 different planning committees using method 3 with 8 animals. Great! Now we're going to look at one last method the animals could use to choose the party committee. They're just going to choose one out of the 8 animals, and that animal will choose the other 2 members. To choose the committee chair, they are going to vote using this ballot. Each of the 8 animals vote for an animal to chair the committee. They are allowed to vote for themselves. Here is an example of one way the vote can turn out. And here are the results. The anteater wins with 3 votes. The beaver, coyote, duck, eagle, and gorilla all have 1 vote, and the flamingo and the hare have 0 votes. Note that the total vote count is 8. Every animal votes for 1 animal, so the sum must be 8. Here's another way the animals might have voted. The animals voted differently this time. To see this, we only have to look at the anteater's vote. He voted for duck this time, but he voted for himself last time. So this is a different vote, but the result is the same. The anteater wins with 3 votes. The beaver, coyote, duck, eagle, and gorilla have 1 vote, and the flamingo and the hare have 0 votes. We can figure out the number of possible votes. There are 8 animals, and since each animal has 8 choices, we multiply 8 to itself 8 times. But that's not what we want to know. What we want to know is the number of possible results. Maybe we can do the same thing as in method 3. We determined that each possibility in method 3 corresponded to 6 possibilities in method 2. So all we had to do was to divide our answer for method 2 by 6, and that was our answer for method 3. But this doesn't work, and let's look at why. One possible result is that duck wins with all 8 votes. There's only one combination of ballots that will give this result. Every animal votes for the duck. Now, here's another possible result. This is an 8-way tie, 1 vote for each animal, and there are 40,320 possible combinations of ballots that give this result. It's the same calculation as when they were all lining up outside the Duomo. 8 possibilities for the anteater's vote times 7 possibilities for the beaver's vote times 6 possibilities for the coyote's vote, and so on. So now we see the problem. The number of combinations of ballots is different for different results. This method of solving the problem is not going to work. In order to solve this problem, we'll have to think of it in a different way. And the way we're going to do it is by inventing a secret code. This code will transform the set of results into a set that we can easily count. To encode our vote result, the first thing we need to do is put the results in alphabetical order. Great. We know the names of the animals, so we just have to look at the number of votes. Here's the code. We write an X for each vote and an I when we move from one animal to the next. Here's an example. The anteater has 3 votes, so we start with 3 X's, 1 for each vote. Then an I because there are no more votes for the anteater. 1 vote for the beaver, so 1 X, followed by an I. 1 X and an I for the coyote, then the duck, and then the eagle. Flamingo has no votes, so there are no X's, but just an I. The gorilla has 1 vote, so an X and then an I, and hare has no votes, so no X's. We don't put an I at the end. Remember, the I means to move on to the next animal. But since the hare is at the end, we do not need to put an I for him. So that's how to convert the result of the vote into this code. One way this is useful is we can actually go back. Let's look at this code. To change the code into a vote result, we need to read from right to left. An I means to move to the next animal, and an X is a vote for the current animal. Pause the video here and see if you can find out how many votes each animal got. Remember, we ordered the animals in alphabetical order. The first letter is I, so we move from the anteater to the beaver. There were no X's before we moved, so the anteater got 0 votes. 1 X means the beaver got 1 vote, then an I. The coyote got 1 vote, and then we move on to duck. There are 4 X's for duck, so we give him 4 votes, then we move on to eagle. There are no X's, so we move on to flamingo. There are no X's for flamingo either, so we move on to gorilla. We have 1 X for gorilla, then we move on to hare, and we finish it off with 1 X on hare. This code will always have 8 X's because there are 8 different votes. And since there are 8 animals, we move to the next animal 7 times, so there are 7 I's. Any string containing 8 X's and 7 I's is a valid code. We can convert it to a vote result using the process we just described. Any vote result has a code that maps to it, and different codes map to different vote results. So the number of codes is the same number of vote results. Now we just need to count the number of codes. A code consists of 8 X's and 7 I's, a total of 15 letters. We can choose the location of the 7 I's, and all the rest of the letters have to be X's. How many ways are there to choose 7 locations for the I's out of the 15 locations? And guess what? We've already solved the same problem, just with different numbers. Pause the video here and figure out which calculation we did that's just like choosing 7 locations for the 15 possible locations. Remember when we wanted to choose 3 of the 8 animals to be on the party committee? That was method 3. And now we have the same thing with different numbers. Instead of choosing 3 of the 8 animals, we are choosing 7 of the 15 locations. Pause the video while you do the calculation. You might want to use a calculator. Each of the 8 animals vote, so we have 8 X's. To separate who the animals voted for, we have 7 I's. This gives us 15 letters to place in order. If we were to place 15 letters in a row, we would have 15 factorial different ways to line up the letters. If they were different letters, we would be done here. But 8 of the letters are the same, the letter X, and the other 7 are the same as well, the letter I. Now here's the trick. Let's say that the animals voted and gave us the following code. The order of the X's don't really matter. We can switch one X with the other and the code would be the same. Same thing for the I's. So we can divide by how many ways we can line up just the X's and how many ways we can line up just the I's. So since we have 8 X's, we have 8 factorial ways we can line up just the X's. And since we have 7 I's, we have 7 factorial ways to line up just the I's. Because the orderings of the X's don't change the code, nor do the orderings of the I's change the code, so we can take the total number of ways we can line up 15 letters, 15 factorial, and we can divide it by the ways to line up just the X's and the ways to line up just the I's. Doing the calculation of 15 factorial divided by 8 factorial times 7 factorial gives us 6,435 ways to vote for the committee chair using method 4. Now that we have 4 different methods of choosing our party committee, they have created the party, and everybody has fun at their party. So, how did you do? These problems were really tough. These problems were pretty tough. Let us know. And thanks for watching. Have a great day, and hope you guys are doing well. Bye-bye.